This is going to be part 4 of the amine chapter. All right, this reaction, you have seen it before. You saw it in the derivatives of carboxylic acids. But we have a little bit of a problem making secondary and tertiary amines, and this one is actually a good way of making secondary and tertiary amines. Of course, we can make primaries, but listen what's happening. I have an acyl chloride, the most reactive carbonyl of organic chemistry, and if I use ammonia, I'm going to make a primary amide. If I reduce the carbonyl with lithium aluminum hydride, we have seen this reaction before, we get rid of the carbonyl and we have a primary amine as the product. Okay, so now you're saying, I know a ton of ways of making primary amines, but I get a primary amine because we used ammonia. If you use a different amine, if you use a primary amine, like this one right here, so you do the first acylation reaction. Notice that now your nitrogen has 2 carbons attached to it, so when I get rid of the carbonyl, I make a secondary amine. So this is the acylation reduction reaction, and it's a very good way of making amines. Secondary amines and tertiary amines. Let's see this again, but let's use a secondary amine right here. Here it is. With your secondary amine, this is a tri-substituted nitrogen right here, a tri-substituted amide. So when we reduce the carbonyl, we make a tertiary amine. So this is an excellent way, easy as can be, of making tertiary and secondary amines. This is another thing that we have seen before. Now, this is aniline, and you and I know that aniline, because it has that lone pair of electrons, it's a very strong activator, so this ring right here is very electron rich. So if I was to chlorinate it, notice I don't even need my iron trichloride, I don't need a catalyst. Actually, if I could cut in reactivity, that would be great, because the ring is so active that I end up with 3 chlorines attached to it. So, too active, how can we cut on the reactivity? Well, here's what happens to an aromatic amine if you add an acyl chloride. It's like the previous reaction that we did, the acylation of the nitrogen. So you take an acyl chloride, and we're going to react it with the nitrogen. Now this nitrogen, it's still an activator. What happens is that it's not as activating as the NH2 that I had to begin with, as the NH2 and aniline, because this lone pair can be delocalized to the ring, or it can be delocalized towards the carbonyl. So now I have reduced the reactivity of the benzene ring. So if you were to compare those two, this one, the aniline, is going to be more reactive. This ring is still an activated ring, but it's less reactive than aniline. So let's do a reaction with this. Let's put something on the ring. So I'm going to take my amide and I'm going to chlorinate it. Notice I still have an activated benzene ring because I don't need the iron trichloride to carry out the reaction. But instead of putting 3 chloride ions on, I put only 1 of them. So only the monochlorination. And if I wanted to hydrolyze my amide, you can do it under acidic or basic conditions. They chose the basic conditions here, so you get your aniline back. So if you wanted to chlorinate or brominate aniline, you have to put a carbonyl on the nitrogen. Then you can do your halogenation reaction, and then you hydrolyze your amide back to the amine. If you're worried about what happened to the carbonyl, since this is a hydrolysis reaction, remember, after you hydrolyze under basic conditions, well, you neutralize it. If you add the acid right there, you'll get the acetic acid. You'll probably protonate that too. If you want to do a Friedel-Crafts acylation, with this one. Remember, this is a bulky group, but it's an activator. So it's an orthopara director. And it is bulky, so whatever I put on there is going to prefer to go to the para position. That's why the chloro ended up in the para position. And once you do your Friedel-Crafts calculation, you can get rid of the amide part. This is a ketone. Nothing's going to happen to the ketone under basic conditions, but I'm going to hydrolyze the amide back to the amine. All right. This is a very interesting part. I know it has 1, 2, 3, 4, but we're going to start right here. This is a reaction that we're going to be studying. This right here is an arene diazonium salt. And when you have an arene diazonium salt, what you basically have is a nitrogen molecule that's ready to go. It is ready to go. So it's an excellent leaving group. And you can substitute it for a bunch of different reagents depending on what you want to put out there. But let's just first see how this happens, the mechanism of this. By the way, for those of you who don't remember, I know that a lot of you remember, but this is sodium nitrite. So nitrite, NaNO2. All right, so you take your amine, and when you add the sodium nitrite, it's going to form nitrosonium ion in there. And we're going to attack the nitrogen, and we add the nitrosonium ion to my nitrogen. Of course, the nitrogen is positive, so I need to deprotonate it, and this is a nitrosoamine. Once you get your nitrosoamine, you still have acidic condition, so we go to step 2. The oxygen is going to get protonated, and once you get that oxygen protonated, we deprotonate the nitrogen. First, let's do a resonance right here. So what we're going to be doing is that we're going to be moving this double bond to in between the nitrogens. All right, so we move the double bond. Now the OH is neutral. The nitrogen here is positive, and I need to get rid of that hydrogen. So I have plenty of water to get rid of that hydrogen. Break the double bond and give the electrons to nitrogen. We're almost there. I have a double bond. Can you see that? I have a double bond in between the nitrogens, and now I need to get rid of the OH. How do we get rid of the OH if we have acidic conditions? We protonate it. Apparently I don't have the next page. You protonate the OH and it leaves. All right, so these are the reactions. Once you actually have your leaving group on your benzene ring, the benzene ring can have anything else attached to it, but the N2 is going to be the leaving group. So that's why they put arene right here. I can substitute it for different things, like for an OH, for a halide, for a cyanide. If you want a fluoride or an iodide in there, you can do it. If you want to put back a hydrogen, you could do it. Or if you want to actually put two rings together, joining them by the nitrogen. So this would be to make dyes in here. So all these reactions can be done. So for example, if you take your arene diazonium salt and you add water to it, they have proposed this as an intermediate. The leaving group leaves. I'm going to put the 3 double bonds. And now this is an empty sp2 orbital. And I have water in solution, so the water would attack. I'm going to put H2O backwards. And then you deprotonate it. and you get the hydroxide after you deprotonate with more water. There's water in solution, deprotonated. But I want you to notice this because it's a good leaving group. It leaves, that's an empty sp2 orbital, and it can be attacked. These two reactions right here with copper, we're going to see it in the next slide. They have a name, and they're the Sandmeyer reactions. And the copper, it's actually going to facilitate the presence, the substitution for the halides. If you use H3PO2, you put a hydrogen back to it. And if you just add a different ring to it, let's just put something else, I don't know, a bromide or an NO2. So you will join them together by the nitrogen group. All right, the Sandmeyer reaction. We react first with sodium nitrite to make the arene diazonium salt. So we're going to make this right here with this molecule. Only one ring is aromatic, so that would be the only ring that makes the arene diazonium salt. And with copper chloride, I can substitute the N2 for a chloride. With copper bromide, I substitute the N2 for a bromide. And with copper cyanide, copper nitride, I can substitute the N2 for the cyanide group. The yields are 75, 90, and 70. So it can be a very good yield or it can be a decent yield. And this is again the Sandmeyer reaction because those are the ones that have the copper. So the exchange is going to be facilitated by the presence of the copper salt. That's it. That's the chapter of amines. Now I need you to work problems. So go to the back of the book and then go to Sapling and start doing problems.